Okay, dear students, today we have discussed about the passband digital transmissions. So, our previous lecture in baseband pulse transmission, we have studied the data is represented in the form of discrete PAM signal, which is transmitted directly over a low pass channel. So in that there is ISI and some channel noises occur which we reduce by the pulse shaping. In digital passband transmission, the incoming data stream is modulated on a carrier with fixed frequency limited imposed by the band pass channel of interest. So in passband digital transmission, we used a modulation and modulate this digital data over a sinusoidal carrier, and the channel nature is band pass. So here we use some type of switching uh, which include the amplitude, frequency and phase, which switch the amplitude, frequency and phase of the sinusoidal carrier in some fashion accordance with the incoming data. So there are three basic schemes we studies further. So in this chapter we study the digital passband transmission technique, which emphasize in two issues. First, the optimum design of the receiver in the sense that it makes fewer error in long run than any other receiver. So this is our first issue. And the second, we calculate the average probability of symbol error of the receiver. And third issue is spectral properties of the modulated signal. So there is two different cases we consider in the study. First is coherent receiver and the non-coherent receiver. In what is coherent receiver? In a coherent receiver, the receiver is in phase lock to the transmitter. So receiver and transmitter both are phase lock conditions. Whereas in non-coherent receiver, there is no phase synchronization between the transmitter and the receiver. So before we go into the detail, we just firstly define the word how the error is estimate, how the signal is estimated at the receiver side. So here is the block diagram. There is some message source which generate message. So what is the here? A message source emits the one symbol every t second with symbol belonging to the alphabet M. So we denote the M1, M2 up to Mn symbols, which is generated by this message source. And consider that we take some example. There is two digital computer, one computer acting as a source and calculate outputs and observe and feed into it, and the resulting computer output is expressed in the sequence of 0, 1 which are transmitted to the second computer over the communication channel. So we use two symbols 0 and 1. In second example we use the quaternary PCM alphabet 0, 0, 0, 1 was 0 and 1, 1, the combination of the two symbols. So in any event, a priori probability P1, P2 and PM specify of the message source output. So there are M messages, so each one have their own probability of occurrence. In the absence of prior information, it is customary assume that the M symbols of the alphabets are equally likely. What is the meaning of that? All symbol which is generated by the source is have equi probable, and the total probability is the probability of that each symbol is 1 by M. Then the transmitter take this message source Mi, this Mi, and codes into the distinct signal SIT suitable for the transmission over the channel. This is the some type of modulation. We just right now define that. Okay, for in passband digital transmission, we use some types of modulation for, and it's done by using a sinusoidal carrier. So the signal is converted to a SIT. So due to the sinusoidal, uh, which we use the geometrical representation. Sorry. So here the signal SIT occupy the full duration allotted to the symbol MI. So SIT is our real valued energy signal as shown by EI 0 to T SI square T dt. So he this SIT is represented by the real valued energy signal. Then this signal goes to the channel. So channel is assumed to have the two characteristics. First, the channel is linear with a bandwidth that is wide enough to accommodate the transmission of SIT with a negligible or no distortion. Second, the channel noise WT is a sample function of a zero mean wide Gaussian noise process. So the noise we introduce here, channel noise, is our thermal noise. It's our zero mean wide Gaussian noise. So with such a channel, we know that the noise is occurring in the form of additive. So it is additive wide Gaussian noise channel. So accordingly, this XT is this SIT plus WT. So what is the task of this receiver in digital communication system? The receiver has observed the received signal xt of the duration t second and make the best estimate of the transmitted signal SIT or equivalently the symbol MI. If the symbol MI is transmitted, then it estimated the MI cap, the best estimation of that symbol at the receiver side to identify the correct signal. So in however the owning of the presence of the channel noise, the decision making process is statistical in the nature, with the result that the receiver make occasional error. The requirement is therefore to design a receiver so to minimize the average probability of symbol error, which is defined as average probability of symbol error for all the symbols. We just find out the actual transmitted symbol by using this. So where MI is our transmitted symbol and M cap is our estimated produced by the receiver, and P M cap not equal to MI by MI is the conditional error probability given that ith symbol was sent. So the resulting receiver is said to be optimum in the minimum probability of error sense. So and this is our model how this noise is occur added with the transmitted signal. So this is the simple work in the digital communication, how the receiver behaves. So especially in the passband transmission model, we assume the same things. We assume that there is some message source which emit one symbol every ts seconds and symbol belonging to the alphabet of M symbols, which we denoted by M1, M2 up to Mn with a probability PM1, PM2 up to PMM specify the message source output. So we show here the OM symbols are equally likely, so all of have the equal probability. So this M array output of the message source is present to the signal transmission encoder. So here is the diagram of especially for the passband data transmission system: message source, signal encoder, modulator, communication channel, detector, and signal transmission decoder. So first this MI symbol is generated by source, which all the symbols are equiprobable as we assume. So this is present to the signal transmission encoder, and signal transmission encoder producing a corresponding vector Si made up of the n real element, one such set of each of the M symbols of the source alphabet, and the dimension n is less than or equal to M. What is the meaning of that? Signal transmission encoder receive MI signal and generate a SI signal in the vector form. Here is S in the dark shade, it means it represents the vector. So for each I signal it represents some vector. So for all the signal there is some table type occur in the vector form. So with vector SIT as input, the modulator then the constructor distinct, and this SI signal corresponding to MI signal is modulated and the carrier wave is changed according to this input signal, and the SIT signal is occurs. SIT signal is occurs, and we know that the signal SIT is our real energy signal, which is represented by these terms. So SIT is our real valued energy signal. So one such signal is transmitted every TS second. So one such signal transmitted every TS second. The particular signal chosen for the transmission depend on the some fashion of the incoming message and the possibility of the signal transmitted in the preceding time slots. So here we use a sinusoidal carrier. So the feature of sinusoidal carrier either is amplitude, frequency or phase is changed according to the uh, input SI, which is depends on the what is the message source, generate the digital data either 0 or 1. So this is the transmission part, and this SIT goes to the communication channel. So here we also assume that there is two characteristics of channel. The channel is linear, it means the bandwidth is wide enough to accommodate the transmission of the modulated signal SIT with negligible or no distortion. Second, the channel noise WT is a sample function of wide Gaussian noise process with zero mean and power spectral densities n naught by 2, where n naught is the noise power. The assumption made here are basically same as we discussed earlier two slides and digital communication. The receiver has which consists the detector, follow the transmitter detector, perform the two function. So what is the function of detector and signal transmission decoder? It reverses the operation performed by the transmitter. It minimizes the effect of channel noise on the estimated M computed for the transmitted symbol MI. So this is our digital passband transmission channel model, how the system works. So here is just review how the modulation system is works: source encoder, channel encoder, modulator, channel demodulator, source decoder, destination. Here are the few things we just remind. What is the channel capacity? The maximum rate at which data can be transmitted over a given communication path or channel under given condition. What is data rate? Rate at which data can be communicated. Impairment such as noise, limited data rate that can be achieved. Bandwidth, the bandwidth of the transmission signal is constrained by the transmitter and nature of the transmission medium. Noise, it is impairments on the communication path. Error rate, what is the error? Transmit 1 and receive 0, or transmit 0 and receive 1. So reason of choosing encoding techniques, digital data, digital signal, equipment less complex, less expensive than digital to analog modulation. Analog data, digital signal. It's permit use of the modern digital transmission and the switching equipment. Digital data and analog signal. Some transmission media will only propagate analog signal. Analog data, analog signal. Analog data in electrical form can be transmitted easily and cheaply like AM radios. So here is this just a radio transmitter and radio receiver for a digital data. Digital modulation convert into its analog signal, and then it's modulated and transmitted at the receiver side. This analog signal is again estimated, and we just find the correct digital data at the radio receiver. So for in digital terms, we just define the what is modulation. It's convert the digital or analog information to the waveform which is suitable to the transmission over a given medium. So for general sinusoidal, there is three parts: amplitude, frequency, and phase. So if the information or source information which is in the form of digital, so it's changing either any one of the parameter, either amplitude, frequency, phase. If one parameter change, other two is kept constant. So if the signal is digital changing parameter, so there is three type of digital modulation technique is occurs. First is amplitude shift keying, second is phase shift keying, and third one is frequency shift keying as per the what we change in the sinusoidal carrier. So in digital modulation technique, inputs of modulator is in the form of digital, either 0 or 1, and carrier we use is sinusoidal carrier. And in analog communication, inputs is in also analog form, and carrier is also in analog form. Then we get that time amplitude modulation, frequency modulation, and phase modulation. But here input data is in the form of digital. So here we use a word keying, amplitude shift keying, phase shift keying, and frequency shift keying. So all these are the motivations why we do modulation. We already studied in the class. Smaller antennas, multiplexings, medium characteristic, interference rejection, and simply circuitry. So here we come our digital modulation technique. In this lecture we just give a basic of these three techniques: amplitude shift keying, phase shift keying, and frequency shift keying. So here in this diagram, in amplitude shift keying, only the change of the amplitude with each symbol, and frequency is constant, low bandwidth requirement, and very susceptible to interference. So here in this diagram we see that for 1 there is some sinusoidal is transmitted, for 0 no carrier signal is transmitted, and again for 1 sinusoidal is transmitted. In frequency shift keying, for 1 and 0 there is we use a two different frequency. So for symbol 0, for symbol 1 this is high frequency we use, for symbol 0 we use another frequency, and again for symbol 1 we use high frequency. In phase shift keying, the change of phase with each symbol, it's more complex and robust against the interference. When transmitted 1, then if 0 comes, then the phase is changed, then again 1 is come, then phase is changed. More effectively, for the common diagram here we use for 0 0 in amplitude shifting no data, for 1 1 there is some sinusoidal carrier is transmitted, again 0 no, then transmitted, and so on. In binary phase shift key, for symbol 0 is low represented by low frequency, and for symbol 1 high frequency, again low high according to the input data. And similarly in VPSK there is phase change when the transition occurs between 0 to 1 and 1 to 0. So in mathematically we represent amplitude shift keying as a one binary digital represented by the presence of carrier and constant amplitude. So when we see in the diagrams early waveforms, when binary 1 occurs then carrier is transmitted, and when binary 0 occurs there is no carrier is transmitted. So it is very susceptible to the noise used to transmit digital data over a optical fiber. It is the one of the application. So its another name is on-off keying, because when the 0 occurs, no data is, no carrier is transmitted. So it's on and off keying. So ASK is also known as on-off keying. Frequency is kept constant. So here we get this type of waveform. In Binary frequency shift keying, we already discussed. We use the two frequencies, one frequency is for binary 1 and one another frequency for binary 0. So there is two different frequency near to the carrier frequency. So where F1 F2 are offsets from the carrier frequency Fc, but by equal but opposite amounts. So bandwidth we calculated is 2 F2 minus F1 divided by 2 plus Fb, where Fb is input bit rate. So here in this diagram we represented for binary 1 a frequency is different, and for binary 0 frequency is different. So for 0 it is a lower frequency, and for 1 higher frequency, and 0 again lower frequency, and so on. Similarly, in phase shift keying, there is two level because phase is change. So we uses two phases to represent the binary signal. We already kept in our mind, if one property is changed, another two properties kept constant. So if we change the phase, then the frequency and amplitude is kept constant. So for binary 0, there is AC cos 2 pi fct is transmitted, and for binary 1, and for binary 0 it's changed by plus pi, or in another form minus AC cos 2 pi fct, and bandwidth is equal to the bit rate. So here in this diagram we represent these two. When the transition occurs, there is a change in the phase accordingly at every transition from either 0 to 1. So this is today's, we just discussed the simple passband transmission model and basics of our amplitude ASK, FSK and PSK. In later lecture we discuss in the details and calculate their bandwidth and probability of error as per according to the syllabus. So thank you, and